Hello. Before we begin, a quick note. The Boy to Sleep podcast relies on you and sponsors, which means you will hear a quick advertisement before the beginning of tonight's episode. While the podcast is free, you are welcome to subscribe for just $2.99 per month, which supports the creation of this podcast and gives you an ad-free listening experience. Simply click the link in the show notes from your podcast app. Rest easy. Hello. Welcome to the Bore You to Sleep podcast. The podcast that will hopefully help you get to sleep. I am going to read an open source book, one that is not particularly interesting, but one that is hopefully boring enough to get you to sleep. Tonight's reading comes from The ABC of Atoms, written by Bertrand Russell and published in 1923. This story looks at atoms and how we understood them at the beginning of the 1900s. My name is Teddy, and I aim to help people everywhere get a good night's rest. Sleep is so important, and my mission is to help you get the rest that you need. The podcast is designed to play in the background while you slowly fall asleep. Thank you to everyone who shared their words of gratitude with me during the week, whether it was through the website or your podcast app. One of the most rewarding aspects of this podcast is hearing from all of the listeners who found the podcast beneficial. Firstly, a massive thank you to new subscribers and listeners of the Boy to Sleep podcast. A big thank you to Melissa McKinney for becoming a patron on Patreon. It's the financial support from patrons and subscribers that contribute to the creation of this podcast. Thank you to all the Spotify listeners who took the time to leave a response in the episode Q&A. In the most recent episodes, thank you to K Dubs and Orange Peel for your lovely comments. There were also some amazing reviews from iTunes listeners, Peed Off Purchaser, No Eyelids, and Emily Jades. Thank you to each of you. Certainly some interesting usernames there. Lovely to hear from all of you. Of course, thank you to everyone who reached out via the website. To Carly, Melissa, and David Johnson. Thank you to each of you for your lovely and kind messages. My goal is to keep this podcast free to allow access for everyone, and it's the support from listeners via Patreon and Spotify that allows me to keep bringing out episodes for those who need them. If you find the podcast beneficial, there are a few ways you can support the creation of the podcast. For as little as $2.99 per month, you can become a subscriber and also ensure that you remove any Spotify ads at the beginning of the episode. If that is not possible, and I appreciate that it is not possible for everyone, then an easy way to support the podcast is by subscribing and leaving a review and rating in your podcast app. If you would like, you can always say hello to me at boytosleep.com. And of course, if you know someone out there in need of a good night's rest, please feel free to share the podcast with them so that they can get the rest that they need. In the meantime, lie back, relax, and enjoy the readings. The ABC of Atoms by Bertrand Russell, author of Mysticism and Logic, The Analysis of Mind, etc. Introductory. To the eye or to the touch, ordinary matter appears to be continuous. Our dinner table, or the chairs on which we sit, seem to present an unbroken surface. We think that if there were too many holes, the chairs would not be safe to sit on. Science, however, compels us to accept a quite different conception of what we are pleased to call solid matter. It is, in fact, something much more like the Irishman's definition of a net, a number of holes tied together with pieces of string. Only it would be necessary to imagine the strings cut away until only the knots were left. When science seeks to find the units of which matter is composed, it is led to continually smaller particles. The largest unit is the molecule, but a molecule is as a rule composed of atoms of several different elements. For example, a molecule of water consists of 2 atoms of hydrogen and 1 of oxygen, which can be separated from each other by chemical methods. An atom, in its turn, is found to be a sort of solar system, with a sun and planets. The empty regions between the sun and the planets fill up vastly more space than they do, so that much the greater part of the volume that seems to us to be filled by a solid body is really unoccupied. In the solar system that constitutes an atom, the planets are called electrons and the sun is called the nucleus. The nucleus itself is not simple except in the case of hydrogen. In all other cases, it is a complicated system consisting, in all likelihood, of electrons and hydrogen nuclei, or protons, as they are also called. With electrons and hydrogen nuclei, so far as our present knowledge extends, the possibility of dividing up matter into bits comes to an end. No reason exists for supposing that these themselves have a structure and are composed of still smaller bits. We do not know, of course, that reasons may not be found later for subdividing electrons and hydrogen nuclei. We only know that so far nothing prevents us from treating them as ultimate. It is difficult to know whether to be more astonished at the smallness of these units, or at the fact that there are units, since we might have expected matter to be divisible ad infinitum. It will help us to picture the world of atoms if we have, to begin with, some idea of the size of these units. Let us start with a gram of hydrogen, which is not a very large quantity. How many atoms will it contain? If the atoms were made up into bundles of 1,000,000,000, and then we took 1,000,000,000 of these bundles, we should have about 1.5 grams of hydrogen. That is to say, the weight of one atom of hydrogen is about 1,000,000,000th of 1,000,000,000th of a gram and a half. Other atoms weigh more than the atom of hydrogen, but not enormously more. An atom of oxygen weighs 16 times as much. An atom of lead rather more than 200 times as much. Per contra, an electron weighs very much less than a hydrogen atom. It takes about 1850 electrons to weigh as much as one hydrogen atom. The space occupied by an atom is equally minute. As we shall see, an atom of a given kind is not always of the same size. When it is not crowded, the electrons which constitute its planets sometimes are much farther from its sun than they are under normal terrestrial conditions. But under normal conditions, the diameter of a hydrogen atom is about 100 millionth of a centimeter. A centimeter is about 1/3 of an inch. That is to say, this is about twice the usual distance of its one electron from the nucleus. The nucleus and the electron themselves are very much smaller than the whole atom, just as the sun and the planets are smaller than the whole region occupied by the solar system. The sizes of the electron and the nucleus are not accurately known, but they are supposed to be about 100,000 times as small as the whole atom. It might be thought that not much could be known about such minute phenomena, since they are very far below what can be seen by the most powerful microscope. But in fact, a great deal is known. What has been discovered about atoms by modern physicists is doubly amazing. In the first place, it is contrary to what every man of science expected, and in part very difficult to reconcile with other knowledge and with deep-seated prejudices. In the second place, it seems to the layman hardly credible that such very small things should not only be observable, but measurable with a high degree of accuracy. Sherlock Holmes, at his best, did not show anything like the skill of the physicists in making inferences, subsequently verified from minute facts which ordinary people would have thought unimportant. It is remarkable that, like Einstein's theory of gravitation, a great deal of the work on the structure of the atom was done during the war. It is probable that it will ultimately be used for making more deadly explosives and projectiles than any yet invented. The study of the way in which atoms combine into molecules belongs to chemistry, and will not much concern us. We are concerned with the structure of the atoms, the way in which electrons and nuclei come together to build up the various kinds of atoms. This study belongs to physics almost entirely. There are 3 methods by which most of our knowledge is obtained: the spectroscope, X-rays, and radioactivity. The hydrogen atom, which has a simple nucleus and only one electron, is studied by means of the spectroscope almost alone. This is the easiest case, and the only one in which the mathematical difficulties can be solved completely. It is the case by means of which the most important principles were discovered and accurately tested. All the atoms except that of hydrogen present some problems which are too difficult for the mathematicians, in spite of the fact they are largely of a kind that has been studied ever since the time of Newton. But although exact quantitative solutions of the questions that arise are often impossible, it is not impossible, even with the more complex atoms, to discover the sort of thing that is happening when they emit light or X-rays or radioactivity. When an atom has many electrons, it seems that they are arranged in successive rings around the nucleus, all revolving round it approximately in circles or ellipses. An ellipse is an oval curve, which may be described as a flattened out circle. The chemical properties of the atom depend almost entirely upon the outer ring. So does the light that it emits, which is studied by the spectroscope. The inner rings of electrons give rise to X-rays when they are disturbed, and it is chiefly by means of X-rays that their constitution is studied. The nucleus itself is the source of radioactivity in radium and the other radioactive elements. The nucleus is unstable and is apt to shoot out little particles with incredible velocity. As the nucleus is what really determines what sort of atom is concerned, i.e., what element the atom belongs to, an atom which has ejected particles in radioactivity has changed its chemical nature, and is no longer the same element as it was before. Radioactivity has only been found among the heaviest atoms, which have the most complex structure. The fact that it occurs is one of the proofs that the nucleus of such elements has a structure and is complex. Until radioactivity was discovered, no process was known which changed one element into another. Nowadays, transmutation, the dream of the alchemist, take place in laboratories. But unfortunately, it does not transform the base metals into gold. It transforms radium, which is infinitely more valuable than gold, into lead of a sort. The simplest atom is that of hydrogen, which has a simple nucleus and a single electron. Even the one electron is lost when the atom is positively electrified. A positively electrified hydrogen atom consists of a hydrogen nucleus alone. The most complex atom known is that of uranium, which has, in its normal state, 92 electrons revolving around the nucleus, while the nucleus itself probably consists of 238 hydrogen nuclei and 146 electrons. No reason is known why there should not be still more complex atoms, and possibly such atoms may be discovered someday. But all the most complex atoms known are breaking down into simpler ones by radioactivity, so that one may guess that still more complex atoms could not be stable enough to exist in discoverable quantities. The amount of energy packed up in an atom is amazing, considering its minuteness. There is least energy in the outer electrons, which are concerned in chemical processes, and yield, for instance, the energy derived from combustion. There is more in the inner electrons, which yield X-rays, but there is most in the nucleus itself. This energy in the nucleus only came to be known through radioactivity. It is the energy which is used up in the performances of radium. The nucleus of any atom except hydrogen is a tight little system, which may be compared to a family of energetic people engaged in a perpetual family quarrel. In radioactivity, some members of the family emigrate, and it is found that the energy they use to spend on quarrels at home is sufficient to govern an empire. If this source of energy can be utilized commercially, it will probably in time supersede every other. Rutherford, to whom, more than any other single man, is due the conception of the atom as a solar system of electrons revolving around a nucleus, is working on this subject and investigating experimental methods of breaking up complex atoms into two or more simpler ones. This happens naturally in radioactivity, but only a few elements are radioactive, at any rate to an extent that we can discover. To establish the modern theory of the structure of nuclei on a firm basis, it is necessary to show by artificial methods that atoms which are not naturally radioactive can also be split up. For this purpose, Rutherford has subjected nitrogen atoms and others to a severe bombardment and has succeeded in detaching hydrogen atoms from them. This whole investigation is as yet in its infancy. The outcome may in time revolutionize industry, but at present, this is no more than a speculative possibility. One of the most astonishing things about the processes that take place in atoms is that they seem to be liable to sudden discontinuities, sudden jumps from one state of continuous motion to another. This motion of an electron round its nucleus seems to be like that of a flea, which crawls for a while and then hops. The crawls proceed accurately according to the old laws of dynamics, but the hops are a new phenomenon, concerning which certain totally new laws have been discovered empirically, without any possibility, so far as can be seen, of connecting them with the old laws. There is a possibility that the old laws, which represented motion as a smooth, continuous process, may be only statistical averages, and that, when we come down to a sufficiently minute scale, everything really proceeds by jumps, like the cinema, which produces a misleading appearance of continuous motion by means of a succession of separate pictures. In the following chapters, I shall try to explain in non-technical language what is known about the structure of atoms and how it has been discovered, in so far as this is possible without introducing any mathematical or other difficulties. Although a great deal is known, a great deal more is still unknown. At any moment, important new knowledge may be discovered. The subject is almost as interesting through the possibilities which it suggests, as through what has actually been ascertained already. It is impossible to exaggerate the revolutionary effect which it may have both in the practice of industry and in the theory of physics. Chapter 2. The Periodic Law. Before we can understand the modern work on the structure of the atom, it is necessary to know something of the different kinds of atoms as they appear in chemistry. As everyone knows, there are a great many different chemical elements. The number known at present is 88, but new elements are discovered from time to time. The last discovery of a new element was announced as recently as January 22nd of this year, 1923. This element was discovered in Copenhagen and has been christened hafnium. Each element consists of atoms of a special kind. As we saw in Chapter 1, an atom is a kind of solar system, consisting of a nucleus which has electrons revolving around it. We shall see later that it is the nature of the nucleus that characterizes an element, and that two atoms of the same element may differ as to the number of their electrons and the shapes of their orbits. But for the present, we are not concerned with the insides of atoms. we are taking them as units, in the way that chemistry takes them and studying their outward behavior. The word atom originally meant indivisible, and comes to us from the Greeks, some of whom believed that matter is composed of little particles which cannot be cut up. We know now that what are called atoms can be cut up, except in the case of positively electrified hydrogen, which consists of a hydrogen nucleus without any attendant electron. But in chemistry, apart from radioactivity, there is nothing to prove that atoms can be divided. So long as we could only study atoms by the methods of chemistry, that is to say, by their ways of combining with other atoms to form compounds, there was no way in which we could reach smaller units of matter, out of which the atoms could be composed. Everything known before the discovery of radioactivity pointed to the view that an atom is indestructible, and this made it difficult to see how atoms could have a structure built out of smaller things, because if they had, one would expect to find that the structure could be destroyed, just as a house can be knocked down and reduced to a heap of bricks. We now know that in radioactivity, this sort of thing does happen. Moreover, it has proved possible by means of the spectroscope to discover with delicate precision all sorts of facts about the structure of the atom which were quite unknown until recent years. It was of course recognized that science could not rest content with the theory that there were just 88 different sorts of atoms. We could bring ourselves to believe that the universe is built out of 2 different sorts of things, or perhaps 3. We could believe that it is built out of an infinite number of different sorts of things. But some instinct rebels against the idea of its being built out of 88 different sorts of things. The physicists have now all but succeeded in reducing matter of 2 different kinds of units. One, the proton or hydrogen nucleus, bearing positive electricity, and the other, the electron, bearing negative electricity. It is fairly certain that this reduction will prove to be right, but whether there is any further stage to be hoped for it, as yet impossible to say. What we can already say, definitely, is that the haphazard multiplicity of the chemical elements has given place to something more unified and systematic. The first step in this process, without which the later steps cannot be understood, was taken by the Russian chemist Mendeleev, who discovered the periodic law of the elements. The periodic law was discovered about the year 1870. At the time when it was discovered, the evidence for it was far less complete than it is at present. It has proved itself capable of predicting new elements which have subsequently been found, and altogether the half-century that has passed since its discovery has enormously enhanced its importance. The elements can be arranged in a series by means of what is called their atomic weight. By chemical methods, we can remove one element from a compound and replace it by an equal number of atoms from another element. We can observe how much this alters the weight of the compound, and thus we can compare the weight of one kind of atom with the weight of another. The lightest atom is that of hydrogen, the heaviest is that of uranium. which weighs over 238 times as much as that of hydrogen. It was found that, taking the weight of the hydrogen atom as one, the weights of a great many other atoms were almost exactly multiples of this unit, so that they were expressed by integers. The weight of the hydrogen atom as one, the weights of a great many other atoms were almost exactly multiples of this unit, so that they were expressed by integers. The weight of the oxygen atom is a very little less than 16 times that of the hydrogen atom. It has been found convenient to define the atomic weight of oxygen at 16, so that the atomic weight of hydrogen becomes slightly more than 1.008. The advantage of this definition is that it makes the atomic weights of a great many elements whole numbers, within the limits of accuracy that are possible in measurement. The recent work of F.W. Aston on what are called isotopes, concerning which we shall have more to say at a later stage, has shown that, in many cases, where the atomic weight seems to be not a whole number, we really have a mixture of two different elements, each of which has a whole number for its atomic weight. This is what we should expect if the nuclei of the heavier atoms are composed of the nuclei of hydrogen atoms, together with electrons which are very much lighter than hydrogen nuclei. The fact that so many atomic weights are almost exactly whole numbers cannot be due to chance, and has long been regarded as a reason for supposing that atoms are built up out of smaller units. Mendeleev, and at about the same time the German chemist Lothar Meyer, observed that an element would resemble in its properties not those that came next to it in the series of atomic weights, but certain of other elements which came at periodic intervals in the series. For example, there is a group of elements called alkalis. These are the 3rd, 11th, 19th, etc. in the series. The third group are called earths. There are 8 such groups in all. The 8th, which was not known when the law was discovered, is the very interesting group of inert gases: helium, neon, argon, krypton, xenon, and niton, all discovered since the time of Mendeleev. These are the 2nd, 10th, 18th, 36th, 54th, and 86th, respectively, in the series of elements. They all have the property that they will not enter into chemical combinations with any other elements. The Germans, on this account, call them the noble gases. The elements from an alkali to the next inert gas form what is called one period. There are 7 periods altogether. When once the periodic law had been discovered, it was found that a great many properties of elements were periodic. This gave a principle of arrangement of the elements, which in the immense majority of cases placed them in the order of their atomic weights, but in a few cases reversed this order on account of other properties. For example, argon, which is an inert gas, has the atomic weight of 39.88, whereas potassium, which is an alkali, has the smaller atomic weight, 39.10. Accordingly, argon, in spite of its greater atomic weight, has to be placed before potassium at the end of the 3rd period, while potassium has to be put at the beginning of the 4th. It has been found that, when the order derived from the periodic law differs from that derived from the atomic weight, the order derived from the periodic law is much more important. Consequently, this order is always adopted. When the periodic law was first discovered, there were a great many gaps in the series. That is to say, the law indicated that there ought to be an element with such and such properties at a certain point in the series, but no such element was known. Confidence in the law was greatly strengthened by the discovery of new elements having the requisite properties. There are now only 4 gaps remaining. The 7 periods are of very unequal length. The first contains only 2 elements, hydrogen and helium. The second and third each contain 8. The fourth contains 18. The fifth again contains 18. The sixth 32. And the seventh only 6. But the seventh, which consists of radioactive elements, is incomplete. Its later members would presumably be unstable and break down by radioactivity. Niels Bohr suggests that, if it were complete, it would again contain 32 elements like the 6th period. By means of the periodic law, the elements are placed in a series, beginning with hydrogen and ending with uranium. Counting the 4 gaps, there are 92 places in the series. What is called the atomic number of an element is simply in its place in the series. Thus hydrogen has the atomic number 1, and uranium has the atomic number 92. Helium is 2, lithium is 3, carbon 6, nitrogen 7, oxygen 8, and so on. Radium, which fits quite correctly into the series, is 88. The atomic number is much more important than the atomic weight. We shall find that it has a very simple interpretation in the structure of the atom. And that concludes tonight's reading. I hope you've enjoyed listening to this story, and I'm also hoping that you're a little drowsy. If you're not quite tired yet, please feel free to listen to another episode of the Boy to Sleep podcast. Until next time, good night.